Chapter 5 Wallets. The word wallet is used to describe a few different things in Ethereum. At a high level, a wallet is a software application that serves as the primary user interface to Ethereum. The wallet controls access to a user's money, managing keys and addresses, tracking the balance, and creating and signing transactions. In addition, some Ethereum wallets can also interact with contracts, such as ERC20 tokens. More narrowly, from a programmer's perspective, the word wallet refers to the system used to store and manage a user's keys. Every wallet has a key management component. For some wallets, that's all there is. Other wallets are part of a broader category, that of browsers, which are interfaces to Ethereum-based decentralized applications, or dApps, which we will examine in more details in the Decentralized Applications chapter. There are no clear lines of distinction between the various categories that are conflated under the term wallet. In this chapter, we will look at wallets as containers for private keys and as systems for managing these keys. Wallet Technology Overview. In this section, we summarize the various technologies used to construct user-friendly, secure, and flexible Ethereum wallets. One key consideration in designing wallets is balancing convenience and privacy. The most convenient wallet is one with a single private key and address that you can reuse for everything. Unfortunately, such a solution is a privacy nightmare, as anyone can easily track and correlate all your transactions. Using a new key for every transaction is best for privacy, but becomes very difficult to manage. The correct balance is difficult to achieve, but that's why good wallet design is paramount. A common misconception about Ethereum is that Ethereum wallets contain Ether or tokens. In fact, very strictly speaking, the wallet holds only keys. The Ether or other tokens are recorded on the Ethereum blockchain. Users control the tokens on the network by signing transactions with the keys in their wallets. In a sense, an Ethereum wallet is a keychain. Having said that, given that the keys held by the wallet are the only things that are needed to transfer Ether or tokens to others, in practice this distinction is fairly irrelevant. Where the difference does matter is in changing one's mindset from dealing with the centralized system of conventional banking, where only you and the bank can see the money in your accounts, and you only need convince the bank that you want to move funds to make a transaction, to the decentralized system of blockchain platforms, where everyone can see the Ether balance of an account, although they probably don't know the account's owner, and everyone needs to be convinced the owner wants to move funds for a transaction to be enacted. In practice, this means that there is an independent way to check an account's balance without needing its wallet. Moreover, you can move your account handling from your current wallet to a different wallet if you grow to dislike the wallet app you started out using. Note: Ethereum wallets contain keys, not Ether or tokens. Wallets are like keychains containing pairs of private and public keys. Users sign transactions with the private keys, thereby proving they own the Ether. The Ether is stored on the blockchain. There are two primary types of wallet, distinguished by whether the keys they contain are related to each other or not. The first type is a non-deterministic wallet, where each key is independently generated from a different random number. The keys are not related to each other. This type of wallet is also known as a JBOK wallet, from the phrase just a bunch of keys. The second type of wallet is a deterministic wallet, where all the keys are derived from a single master key, known as the seed. All the keys in this type of wallet are related to each other and can be generated again if one has the original seed. There are a number of different key derivation methods used in deterministic wallets. The most commonly used derivation method uses a tree-like structure, as described in the hierarchical deterministic wallets BIP32, BIP44 section. To make deterministic wallets slightly more secure against data loss accidents, such as having your phone stolen or dropping it in the toilet, the seeds are often encoded as a list of words for you to write down and use in the event of an accident. These are known as the wallet's mnemonic code words. Of course, if someone gets hold of your mnemonic code words, then they can also recreate your wallet and thus gain access to your Ether and smart contracts. As such, be very careful with your recovery word list. Never store it electronically, in a file, on your computer or phone. Write it down on paper and store it in a safe and secure place. The next few sections introduce each of these technologies at a high level. Non-deterministic random wallets. In the first Ethereum wallet, produced for the Ethereum presale, each wallet file stored a single randomly generated private key. Such wallets are being replaced with deterministic wallets because these old-style wallets are in many ways inferior. For example, it is considered good practice to avoid Ethereum address reuse as part of maximizing your privacy while using Ethereum, i.e. to use a new address which needs a new private key every time you receive funds. You can go further and use a new address for each transaction, although this can get expensive if you deal a lot with tokens. To follow this practice, a non-deterministic wallet will need to regularly increase its list of keys, which means you will need to make regular backups. If you ever lose your data before you have managed to back up your wallet, you will lose access to your funds and smart contracts. The Type 0 non-deterministic wallets are the hardest to deal with, because they create a new wallet file for every new address in a just-in-time manner. Nevertheless, many Ethereum clients use a key store file, which is a JSON encoded file that contains a single randomly generated private key, encrypted by a passphrase for extra security. The JSON file's content will include the following fields: address, crypto, ID, and version. The crypto field will include cipher, ciphertext, cipher params, KDF, KDF params, and MAC. The key store format uses a key derivation function, KDF, also known as a password stretching algorithm, which protects against brute force, dictionary, and rainbow table attacks. In simple terms, the private key is not encrypted by the passphrase directly. Instead, the passphrase is stretched by repeatedly hashing it. The hashing function is repeated for 262,144 rounds, which can be seen in the key store JSON as the parameter crypto.kdfparams.n. An attacker trying to brute force the passphrase would have to apply 262,144 rounds of hashing for every attempted passphrase, which slows down the attack sufficiently to make it infeasible for passphrases of sufficient complexity and length. There are a number of software libraries that can read and write the key store format, such as the JavaScript library Ethereum. Tip: the use of non-deterministic wallets is discouraged for anything other than simple tests. They are too cumbersome to back up and use for anything but the most basic of situations. Instead, use an industry standard-based HD wallet with a mnemonic seed for backup. Deterministic seeded wallets. Deterministic or seeded wallets are wallets that contain private keys that are derived from a single master key or seed. The seed is a randomly generated number that is combined with other data, such as an index number or chain code, to derive any number of private keys. In a deterministic wallet, the seed is sufficient to cover all the derived keys, and therefore a single backup at creation time is sufficient to secure all the funds and smart contracts in the wallet. The seed is also sufficient for a wallet export or import, allowing for easy migration of all the keys between different wallet implementations. This design makes the security of the seed of utmost importance, as only the seed is needed to gain access to the entire wallet. On the other hand, being able to focus security efforts on a single piece of data can be seen as an advantage. Hierarchical deterministic wallets, BIP32, BIP44. Deterministic wallets were developed to make it easy to derive many keys from a single seed. Currently, the most advanced form of deterministic wallets is the hierarchical deterministic HD wallets, defined by Bitcoin's BIP32 standard. HD wallets contain keys derived in a tree structure, such that a parent key can derive a sequence of child keys, each of which can derive a sequence of grandchild keys, and so on. HD wallets offer a few key advantages over simpler deterministic wallets. First, the tree structure can be used to express additional organizational meaning, such as when a specific branch of subkeys is used to receive incoming payments, and a different branch is used to receive change from outgoing payments. Branches of keys can also be used in corporate settings, allocating different branches to departments, subsidiaries, specific functions, or accounting categories. The second advantage of HD wallets is that users can create a sequence of public keys without having access to the corresponding private keys. This allows HD wallets to be used on an insecure server or in a watch-only or receive-only capacity, where the wallet doesn't have the private keys that can span the funds. Seeds and mnemonic codes, BIP39. There are many ways to encode a private key for secure backup and retrieval. The currently preferred method is using a sequence of words that, when taken together in the correct order, can uniquely recreate the private key. This is sometimes known as a mnemonic, and the approach has been standardized by BIP39. Today, many Ethereum wallets, as well as wallets for other cryptocurrencies, use this standard, and can import and export seeds for backup and recovery using interoperable mnemonics. To see why this approach has become popular, let's have a look at an example. A seed for a deterministic wallet in hex, FCC:137. A seed for a deterministic wallet from a 12-word mnemonic, wolf, juice, proud, detail, hub. In practical terms, the chance of an error when writing down the hex sequence is unacceptably high. In contrast, the list of known words is quite easy to deal with, mainly because there is a high level of redundancy in the writing of words, especially English words. If inzect had been recorded by accident, it could quickly be determined, upon the need for a wallet recovery, that inzect is not a valid English word and that insect should be used instead. We are talking about writing down a representation of the seed because that is good practice when managing HD wallets. The seed is needed to recover a wallet in the case of data loss, whether through accident or theft. So keeping a backup is very prudent. However, the seed must be kept extremely private, so digital backups should be carefully avoided, hence the earlier advice to back up with pen and paper. In summary, the use of a recovery word list to encode the seed for an HD wallet makes for the easiest way to safely export, transcribe, record on paper, read without error, and import a private key set into another wallet.